Hi guys, so today we'll be solving Leetcode question. Smallest range covering elements from k-list. So we're given a k-list of sort integers, right, in non-decreasing order. We need to find the smallest range that include at least one number from each of the k-lists. We define the range AB is smaller than range CD if the difference between B minus A is smaller than D minus C, or A is smaller than C if B minus A is equal to D minus C. So basically, if the difference is smaller, then the range is smaller, and in the case if the difference is equal, then we will need to compare the first element in the range, right? Okay, so let's take a look at this example. We have a 3 sorted list. Here the output is 20, 24, and in the list 1, 24 is in range 20, 24. List 2, 20, list 3 and 22, right? So 20, 24 is the result for this example, and it has a difference of 4, right? And then okay, so for this example, here in this example, then we can see that we can have duplicate in each of the k lists, right? So here we have 1, 2, 3 in all 3 groups, and hence the result is 1 and 1 because the difference is 0, right? And it cover in all the 3 groups, then we have 1. Okay, so how can we do this? How can we go about doing this? The first intuition is that we can actually merge all of these guys into one big array, right? That can make it a little bit more easy to actually visualize what is happening. Okay, so once we group all this guy into one big array, then we need to sort them, right? And once we sort them, then we will basically implement a sliding window technique, and then we will keep incrementing our rack boundary, right? We have our left and our right boundary. We keep increment our right boundary up until we find until a point where we have all of the elements from different groups in our window, right? So that's basically one candidate for the result. We have one big array. We sort them, right? We need to sort them, and then we set our boundary, left boundary and right boundary all at 0, and then we keep on incrementing our right boundary up until where a point where in our window we have all of the elements from all of the groups, right? Not all elements, but one of the elements from each group. And then what are we going to do next? We're going to keep on incrementing our left pointer to see if incrementing our left pointer actually lead us to basically a range that is smaller, right? And we keep on doing that. So the key point here is how can we tell if our sliding window cover at least one number from each of the group. Basically that's hash table, right? It's easy to tell, and this problem is actually basically the same as this guy. Minimum window substring. if you have already done this, then it's basically the same things, right? But here, and we are given a string. Here we are given k sorted list, right? So we need to basically concat them into one big sorted array before applying this algorithm, right? So here, what we're going to do first, we are going to say that n is equal to len nums, and then we're going to create our sort big array, right? Here, and then we're going to use for I in range len nums ren right, ren, and then for n in nums I, what we are going to do is that we are going to insert into our merged list. What are we going to insert into our merged list? Are we going to just insert our n? Basically, it's not going to be enough, right? Because we also need to keep track of the group. What group does this number belong to, right? So instead of just passing into the value, we're going to passing into the index of the group also, right? That's I. After that, you're going to sort our merge list. Okay, so that's basically the first half of the algorithm. And now, what are we going to do next? We're going to initialize a hash count. Right, the hash count. This is going to tell us the number of element in each group for a window, for the state of the window that we are currently in, right? So first we're going to set our left and right pointer all at 0, and then for the first window, we need to increment the hash count of the element at the first index, right? Merge I, that's basically merge 0, and then we need to take the group. What is the group index? Right, it's at 1. So we're going to say merge 0, 1, merge 1. Okay, so we need to have to store our result in the form of a list with 2 elements, the start and the end. Okay, so how are we going to deal with this? Basically, it's up to your preference, but I'm going to do this. This is going to be the end point, and what is the start point? The start point I'm going to set to merge 1, 0 plus 1. Why? Because when we apply our sliding window technique, there will be a point where we meet a candidate, right? For a given example, except because the list cannot be empty, right? If you read the constraint, the list cannot be empty. Okay, the list cannot be empty, so the list is always going to be like from 1 to up until 15, right? And by that, then we are going to always going to have a result. And then the first result we set here, basically, if we have a result and we compare it with this guy, then it's always going to take the position of this guy. Why? Because if we take the n minus the start, we're going to get float infinity. That's always going to be bigger than anything, right? And then if okay, so that's it, right? And then what are we going to do next? We are going to implement our sliding window technique. If y are smaller than length of merge, right? And then y the length of hash count is equal to the length of nums, which means right. Okay, so if let's say if b minus a is smaller than b minus c, if result 1 minus result 0 is actually larger than merge R0 minus merge L0, or in the case that is equal, right? In the case that it is equal, then and result 0 is larger than merge L0, we are going to update our result. Result is going to be equal to merge L0 merge R0, right? Okay, so here we're going to be greedy, right? We're going to be greedy, and let's say that this window can be smaller, and we can achieve a better result by experimenting, incrementing our left pointer, right? So let's say if we are going to shift our left pointer 1 unit ahead, 1 index by 1 index to the right, then we will need to decrement our hash count merge L1, which is the group of the element at L index, right, by 1. But here's the key point: if we're going to decrease it, but the value is 0, what will happen? Then our hash count, the length of our hash count could be reduced, right? It could be reduced to something that is smaller than the length of nums, which means we don't have enough element from each group. And if that's the case, then we're not going to increment our left pointer, right? So if this is the case, then we are not going to increment our left pointer. But if that is not the case, if hash count merge L1 minus 1 is actually larger or equal to 0, then we're going to decrease it minus 1, and then we're going to shift our left pointer. Okay, else we're going to break it, right? Okay, so now what we're going to do next, we are always going to increment our right pointer at the end of each while loop, right? And then basically hash count merge if L plus 1 is smaller than len merge hash count merge no, not L plus 1, R plus 1, R plus 1 plus 1, sorry. Right, and then do this. First we just return result. That's basically oh my god, what the hell. Merge all, merge all. Oh, here, sorry. Okay, so that's it. That's basically it, right? Okay. Max number of test case. If we have only one element. Merge 1, 0 plus 1. Not merge on, I'm sorry. That's basically this. Basically this can be anything. This can be anything. This can be also be float minus whatever the heck that is. Yep, okay. So this solution is actually linear in oh no, not linear, right? We need to merge it, so that could be time complexity O and log n space complexity O and okay. So I hope it makes sense to you guys. See you guys on next video. Thank you for watching. See. Yeah, no bad.